All right. So this talk is on thresholds in the lattice of subspaces of fq to the n. So let me start by stating the result that we prove, and I'll come back and give all the, define everything carefully. But so here's the result that we prove. So we're looking at the lattice of linear subspaces of fq to the n, where for fq is any finite field. And Q will be any ideal, so downward closed set. And we denote by mu sub k of Q the k subspace density of Q, so just the fraction of k-dimensional subspaces that are contained in Q. So these subspace densities are decreasing with k, and for a non-trivial ideal, so this starts at 1 because Q contains the zero-dimensional subspace, and it's decreasing down to 0. And so our main theorem is the following. So it shows it's an inequality on these subspace densities. It shows that if the kth subspace density is 1 over 1 plus z, where z is any non-negative real, then the k plus first subspace density is at most 1 over 1 plus q times z. Okay, and as a consequence, it gives the following threshold theorem. So it shows that for any epsilon, the number of steps that it takes you to go from above 1 minus epsilon to below epsilon is order of log base q of 1 over epsilon. Okay, so this looks like a very sharp, if you've seen the notion of thresholds in the Boolean lattice, this looks like we're saying that every ideal has a very sharp threshold. Okay, so let me step back and give some background on the Boolean lattice and then the linear lattice, which we studied. So the Boolean lattice denoted P of n. Think of it as power set of n. So this is just the lattice of, that's a typo of, obviously, of subsets of 1 to n, ordered by inclusion. Okay, so there's 2 to the n elements. And we denote by P and K just the set of k-element subsets. And so the linear lattice is sort of the Q analog of the Boolean lattice. So we're considering the finite field FQ. Q here is any prime power. FQ to the n is just an n-dimensional FQ vector space. And LQN is the lattice of linear subspaces of FQN. Okay, and similarly, the kth slice of this lattice is just a set of k-dimensional subspaces. So, on the one hand, the linear lattice LQN is the Q analog of the Boolean lattice. So there's this sort of combinatorial analogy between subsets of a given set and subspaces of a given vector space. On the other hand, LQN is also a sub-poset. As a partially ordered set, it embeds into the Boolean lattice on Q to the n elements. And so a question which arises naturally is, do thresholds of monotone properties in LQN, do they scale like thresholds in the Boolean lattice Pn, or like thresholds in the Boolean lattice of on Q to the n elements or atoms? Okay, so this is the question that we studied. Okay, so let me give some more definitions. So let me first start with the Boolean lattice. So we're considering Q, which is any ideal downward closed set, or you can think of a monotone property in the Boolean lattice. And the way we define formally the k subset density, mu sub k of Q, just the probability that a uniform random k-element set belongs to Q. In other words, this is the size of Q intersected with the k-element subsets of n over n choose k. And as we mentioned, it's easy to show. I believe this follows from the FKG inequality that this is a decreasing sequence of densities in terms of k. And if Q is non-trivial, so meaning non-empty, and it's not all of Pn, well, then there's some unique threshold T, which I'll denote also by T, the critical threshold at Q, such that at size T minus 1, the density is at least 1/2, and it's strictly less than 1/2 at mu T. Okay, so this passes from above to below 1/2 at some point T. So in the linear lattice, LQ of n, we define everything in exactly the same way. Except now we're looking at the densities of k-dimensional subspaces, okay? And instead of the binomial coefficient here, we have the q binomial coefficient, which I'll define okay. And then once again, it's easy to show that these densities are decreasing in k, and of course there's some threshold for every non-trivial property. So so there's a result in the Boolean lattice known as the Bollobás-Thomason theorem, which is sort of informally stated as every monotone property has a threshold. Okay, so and really what this is it's the following inequality. It shows that not only for any ideal, not only is the sequence mu1, mu2, mu3 decreasing, but in fact, it remains decreasing even if you raise mu k to the power 1 over k, which of course increases it. So we have these inequalities, and this implies that for every epsilon, you pass from above 1 minus epsilon to below epsilon over j minus I steps, which is at most some order of the critical threshold, or in fact you can say the minimum of the critical threshold and n minus the critical threshold, since you can always take the dual ideal anyway. So you can show this, and then moreover the ratio of j over I, and as well as the ratio of 1 minus I over 1 minus j, is at most 1 over epsilon log 1 over epsilon. Okay, so this is what the Bollobás-Thomason theorem says. And there's a notion of a coarse and sharp threshold. So essentially, an ideal has a coarse threshold if it's sort of tight for this theorem, and it has a sharp threshold if it transitions from 1 minus epsilon to below epsilon in very quickly. So in little o of the critical threshold steps. Okay, and another relevant result in the Boolean lattice, and this is actually used to prove. This is used in the proof of the Bollobás-Thomason theorem. Is a very basic result in combinatorics known as the q-Kruskal-Katona theorem. So here we consider a family of k-element subsets of n. Okay, so we're not looking at a full ideal. Just look at a set of k-element subsets of n. The shadow of that family S consists of all k minus 1 element sets which are contained in some element of S. And we can consider a continuous version of the binomial coefficient for any real number x, just defined by the following polynomial. And here's one version that's easy to state of the Kruskal-Katona theorem, that if the size of the family S is x choose k, then the size of the shadow is at least x choose k minus 1. Okay, and this version in terms of the continuous binomial coefficient was originally shown by Lovász, and there's a sort of stability version of this result due to Kivas. And that Kivas's version of Kruskal-Katona was generalized to this linear lattice. So in the linear lattice, for a family of k-dimensional subspaces, we define the shadow in the same way. And now one considers the q binomial coefficient. And when q is an integer, this is counting the number of k-dimensional subspaces of an x-dimensional FQ vector space. And so Chowdhury and Patkos proved the following q analog of the Kruskal-Katona theorem by essentially the same proof. Okay, and using as a corollary of the q-Kruskal-Katona theorem, one can prove a q analog of the Bollobás-Thomason theorem, which I state here. Okay, so this is exactly the same as you have in the Boolean lattice. And in particular, so this implies that every non-trivial ideal has threshold length, which is order of the critical threshold. But right, so in a joint work a few years ago with Akinori Kawachi and Osamu Watanabe, we were looking at this and noticed that in all examples we could come up with, the threshold interval is actually vastly smaller. And in fact, I mean, this led to the following conjecture that for any non-trivial ideal in the linear lattice, the threshold interval has length order log q of 1 over epsilon, independent of the location of the threshold. So in other words, you just over a constant number of steps for any epsilon, you transition from 1 minus epsilon to epsilon. Okay, so this is, and really what this is saying is that the threshold behavior really scales like the Boolean lattice over q to the n elements. Okay, and so so here I've just restated the q-Kruskal-Katona theorem of Chowdhury and Patkos, which was previously known. I'm just stating it in terms of densities. So I'm just dividing by the q binomial coefficients on both sides. And so this result that they proved, they showed that moreover it's tight if and only if x is an integer. Okay. However, this turns out to be slack, and in fact, very, very slack when x is between n minus 1 and n. Okay, so in other words, when the family S has density which is between roughly 1 over q to the k and 1. Okay, so in the case of dense families, this version of the q-Kruskal-Katona theorem was very slack. Okay, and that's where we prove a stronger result. So this is going to be an improvement of the previous Kruskal-Katona theorem when S is dense, has density, at least 1 over q to the k. And it has a very clean statement. So for any family of k-dimensional subspaces and any non-negative real number z, so if the k subspace density is 1 over 1 plus z, then the k minus 1 density of the shadow is at least 1 plus z over q inverse. Okay, and moreover, there's some nearly tight examples. So particular families you can construct, even with constant density, for which this is nearly tight. And the way this is proved, it's actually a very simple proof, just a few pages of calculations. It proceeds as follows. So we consider the Rossman graph. So the vertices of this graph are all the k-dimensional subspaces of fq to the n. And there's an edge between two subspaces A and B whenever the dimension of the intersection is k minus 1. And so for any set S, we denote by phi of S the edge expansion in this graph. And then the expander mixing lemma gives a lower bound on phi of S in terms of the k subspace density, just directly. And this is using known characterization of the eigenvalues of the Rossman graph. And then on the other hand, the Cauchy-Schwarz inequality gives an upper bound on the edge expansion of S in terms of the ratio of the k subspace density of S and the k minus 1 subspace density of its shadow. And when you combine this lower bound with this upper bound, then this inequality pops out. Okay, so this is the theorem. And then as a corollary, this implies that every non-trivial ideal in the linear lattice has threshold interval length, this order log q 1 over epsilon. So this proves the conjecture from the previous paper with Kawachi and Watanabe. And this this result suggests a possible definition, one possible definition of this distinction between coarse versus sharp thresholds in the linear lattice. So if we have a sequence of ideals, Qn, so one for each dimension n, we'd say that it has a coarse threshold if the interval has length omega log q1 over epsilon, and a sharp threshold if this is little o of log q1 over epsilon. Okay, and finally, I'll mention an application of this result to a problem in query complexity. And so this is the problem that was actually studied in that paper with Kawachi and Watanabe, and this is what led us to study this question in the first place. So here's the problem. We want to find a hidden non-zero element. Oh, sorry, a non-zero element in a hidden subspace of f2 to the n. So here A is some adversarially chosen non-trivial subspace of f2 to the n, which we don't get to see. So we get information about A by making queries, and a query is just for any ideal in the subspace lattice. We can ask, does A belong to that ideal? And we get a yes or no answer. Okay, and so we're allowed to make queries, a batch of queries simultaneously, so non-adaptively, and our queries can be randomized. And the goal is to output a non-zero element of A with probability at least 1/2. Okay, so to find some witness in a hidden non-trivial, non-empty, subspace of dimension at least 1. So there's an upper bound of n squared queries, which follows from the valiant Vazirani isolation lemma.
Ben, just
yeah. What's that? Oh, okay, yeah. I'll wrap up in a minute. So and so using our threshold theorem for ideals in the linear lattice, we can show a matching lower bound of omega n squared. And yeah, so this is strengthening a result from that paper. And then this is just summarizing. I just state the result again. We show that ideals in LQN scale like the corresponding ideals in the Boolean lattice on q to the n atoms. And then there's some natural, interesting questions. What's the right notion or useful notion of coarse versus sharp thresholds in the linear lattice? And then can you show Q analogs of results like Friedgood and Friedgood-Colley theorems? So yeah, that's it.
Okay, so thanks for the nice talk. And if anyone has questions, you can please go to the mic. Okay, so if not, in the meantime, I have one question, Ben. So yes. So where is the density assumption used in your result, in your proof?
Oh yeah. Sorry, that comes from the edge expansion. So the edge expansion is based on, this has to do with the density of S, right?
Oh, okay.
Yeah.
And is there any hope that this holds in more generality, like these kinds of results, or do you, like, your conjecture is still open with Kawachi?
No. So it sort of completely settles that conjecture. Yeah, I don't know what other. I haven't thought about other settings for this kind of result, but yeah, no. But it completely answers that question.
Okay, that question is also for dense sets. Okay. So
right.
Thanks a lot, Ben.